Okay, so we understood what enthalpy is in the previous lecture. Now let's try and understand what entropy means. Now, entropy is basically gives you an idea about the irreversibility of the reaction. So this is, if you want to understand in a very broad way, in a very physical way, since it is very difficult to understand physically the concept of entropy, we can understand it by the notion of irreversibility. So that means if a reaction is more irreversible, now what is a reversible and an irreversible reaction? So irreversible process. So this is slightly different from the concept of reversible reactions and irreversible reactions. Okay, this is the irreversible process. So please remember that we discussed the notion of irreversible and reversible processes. How reversible is a hypothetical process in which at all times the pressure inside is equal to the pressure outside. All the system is in equilibrium at all times, and from going from state A to state B, you are going through infinitely small steps in an infinitely long time, right? So that is a reversible process. So what is an entropy? The entropy is the reverse of that, okay? Irreversibility. The more a reaction is irreversible, the more its entropy is. People also define it as disorderness, right? There are two ways of defining it. So let's first focus on the concept of irreversibility, and let's try and go with that, because this will take us in a very different direction, and this will take it in a direction that we would want to go. So if a reaction is more irreversible, that means a reaction is more spontaneous. That means it wants to go in a certain direction, it doesn't want to come back, right? And that is why the reaction is more spontaneous. So if a reaction goes forward but then has no problem coming back, that means that the reaction was reversible, but that means that the reaction was not spontaneous. There is no motivation for that reaction to go forward, right? So if the reaction is basically spontaneous, then only it will be irreversible, right? And only those reactions will have increase in entropy. So let's understand it that way. Like, entropy is basically a reaction which is irreversible, will be more spontaneous, and that is why we'll have more entropy. Okay, that's the physical understanding of the system. How did we came up with this idea of entropy? It's a weird variable. How did we come up with this? We came up with this idea from the steam engine. Right, so there were people who during the 18th century who were trying to find out the maximum efficiency possible for a steam engine. So there was a very young scientist called Carnot. He was like just 28 years old when he came up with this unique, like, fascinating idea. He came up with this idea of a Carnot cycle. You must have read about this. So using the concept of the Carnot cycle, he came up with this idea of the efficiency of, he came up with the idea of the efficiency of a Carnot cycle. So a Carnot cycle basically is work done by the Q, right? So I'm not going into this because it's not entirely related to the entropy, but we have to understand how did we came up with this idea. So when Carnot came up with this whole idea of this Carnot cycle, he could come up with this maximum limit to the efficiency of a steam engine, which was very important for the Industrial Revolution at that time, right? So we wanted to know what is the maximum physical possible limit to getting the steam, the efficiency of the steam engine. So he came up with this idea. Now, when he did all this, there was another scientist called Clausius. So what Clausius saw, that whenever you had any kind of reversible reactions, what he saw, so the change in Q in a reversible reaction divided by over the temperature, he observed that this quantity is conserved. Absolutely fascinating. Like, we know that Q is a path function. It does not depend on the state. But you see, Q by T conserved. What does that mean? That Q by T, that variable, which is basically Q by T is a state function. So Q by T is conserved. That means Q by T is behaving like a state function, like entropy. Like enthalpy, like internal energy. So Q by T is also behaving like a state variable. So then they came up with this, they just said, okay, this variable, whatever that is, which is mathematically equivalent to Q reversible temperature, is getting conserved, and that is why they said, okay, we'll say that this quantity is basically this. So this is the change in entropy. This is how they came up with this idea of entropy. They did not want to complicate things. They wanted to simplify things, right? And that is why they said that, okay, since Q by T is conserved, is the state variable, let's give the name of entropy. So that is how the entropy term came, okay? This is a state function. All right. Now, in here, there are two things that you have to understand. That we'll have to understand this in terms of the reversible reaction and terms of an irreversible reaction. So during a reversible reaction, reversible process, you do not create entropy. You don't create entropy. You just exchange entropy. Energy is entropy. You can exchange entropy. You can exchange S. Right? You can exchange that. And what, from where to where is the exchange happening? So you have a system and you have a surrounding, right? So the exchange is between the system and the surrounding. So if the system gains entropy, the surrounding loses it, and vice versa. So if you come out of the system and see the system and the surrounding together, you can say that the D exchange of the system is equal to negative of the D exchange, so E stands for exchange, of the surrounding, DES of the surrounding, because you're not creating anything, you're just, so if the system is gaining 5 units, whatever that unit is, you can actually calculate it. The unit is kilojoule or joule per mole per Kelvin, right? So if the system gains 5 kilojoules per Kelvin entropy, then the surrounding loses it. So you are just exchanging it. So we know that, okay, the entropy of the universe is basically equal to the change in entropy of the system plus the change in entropy of the surrounding. Now, in a reversible process, this plus this is not changing, right? So there is no change in the D of S of the system or the surrounding. But during an irreversible process, you create entropy. So during an irreversible process, you create entropy, okay? So when you create entropy, you increase the entropy of the system. So the universe is made up of, in the universe, there are many reactions that are happening. So there are reversible reactions going on, there are irreversible reactions going on, right? So in a reversible reaction, the entropy of this universe, which is this plus this, is not changing, it's just getting interchanged. But during an irreversible process, the entropy of the system increases. Therefore, the universe entropy increases, right? Because the universe is made up of system plus the surrounding. So in the universe, there are always irreversible processes happening, right? You are growing, that's an irreversible process, right? Like this, for example. So whatever, like there are so many irreversible reactions happening in the universe, and they are contributing to increasing the entropy of the universe. And that is why there is always the entropy of the universe is always increasing. And this is the second law of thermodynamics. So the entropy of the universe is always increasing. This is the second law, okay, of thermodynamics. Now, the third law of thermodynamics tells us that you can actually find out the absolute value of entropy. So the third law just tells you that the entropy of anything at 0 Kelvin is 0, right? So the third law of thermodynamics is just this, that you can actually calculate the absolute amount of entropy in any pure substance, solid, liquid, or gas. If it's pure, you can actually calculate the entropy of any body, of any pure body, the standard state, at 0 Kelvin. It will be 0. So this is the third law of thermodynamics. Okay, so you understood the third law. Based on the third law, now you understand that you can actually find out the entropy of any system. You can actually find out the exact value, the absolute value of entropy. It's difficult, but it could be calculated. For enthalpy, it is not possible. You cannot get the absolute value of enthalpy. Why? Because it is based on, you calculate enthalpy or based on a reference state, which is the elemental reference state. In here, we know it acts like a reference state in here, but we don't have to assume things. It is true. I mean, for any pure substance, the entropy of that pure substance at 0 Kelvin is 0. Okay? So now, based on this, you can actually find out the delta H and the delta S of different reactions, right? Of different reactions, and we represent this concept with this equation. So if you want to calculate the delta H, the standard delta H of any reaction, what you just do, you sum the delta H of formation at standard of the products. Basically, you also multiply with the stoichiometric coefficients, but you know that. And you delta H of formation of the reactants. In a similar way, you can also write down the similar equations for calculating the change in the entropy. So you can just write delta S not R and things like that. Okay, so you must have read this in aqueous geochemistry in your classes too. Okay. So this is the concept of the delta H and delta. So you understood what H was, enthalpy. You understood what enthalpy was. You understood what entropy is, and then you are able to calculate the change in enthalpy, the delta H of any reaction with this formula. With a similar analogous formula, you can find out the delta the entropy change in this reaction in any reaction. Okay. All right.